Assalamualaikum. Today, we're going to present our group project for radio navigating system with the title of Modeling and Correction of GPS Array using SBAS with comparative analysis of Dgps and EKF. Our group members is Muhammad Zahid, NAFIZ NAJWAN, IQBAL SYARIFUDIN, and Muhammad IMRAN. First, introduction. GPS is a critical in aviation, maritime, autonomous system, and mobile apps. Its accuracy is often reduced by atmospheric delays, satellite clock, multi-part signal reflection. The study focuses on correcting these errors using the main method, which is SBAS, satellite-based augmentation system, with the comparative method, Dgps, differential GPS, and EKF, extended Kalman filter. Our aim is to assess how SBS perform in improving GPS accuracy with DGS and EKF as supporting comparison. The type of GPS errors. The first type is ionospheric delay, tropospheric delay, satellite clock errors, orbital errors, and multi-part errors. These errors may come from satellite and atmosphere, the receiver, and the environment. For the data correction and analysis, the GPS accuracy is reduced by errors from atmospheric, satellite, and also multi-part signal. The correction method used is SBAS, Dgps, and EKF, while the data sources is from the mobile GPS logger apps, the public dataset, and simulated GPS data. For the evaluation process, the first step is the raw GPS data process and compared to the ground truth. And the second step is SBAS, DGPS, and EKF applied individually to the same dataset. And the third step, the accuracy assessed using the mean error, standard deviation, and RMSE. The fourth step is the visual plots created to track error over time. The result for each method, performance evaluated independently and comparatively under varying conditions. And the third one, the solver method performance summary. The method that used is SBAS, DGPS, and EKF. The accuracy for the SBAS is 1.5 to 2 meter, DGPS is 0.9 to 2, and the EKF from 1 to 3. The best condition for SBAS, DGPS, and EKF is when the open sky aviation, DGPS is within 100 to 300 distance, EKF with the urban canyons or tunnels, while the limitation for SBAS is not effective for multi-part urban limit. DGPS is accuracy drops within distance, and EKF is required motion sensors. SBAS and DGPS efficiently reduce common GPS error. EKF adds robustness by maintaining smooth tracking during signal outage. It is ideal for dynamic or obstructed environment. Next, I will pass the next slide to my friends.
Let's move on to development of error model. So, here we will use to understand the mathematical model of source of GPS error, and of course we have to know the pseudo range formula. So this is the pseudo range formula. So it's used for precise modeling is vital for Sbas correction, algorithm, and system reliability. And let's see the satellite. So there's a few of error models. So we have satellite clock drift modeling, we have ionospheric delay modeling, tropospheric delay modeling, and also we have multi-part and receive noise modeling and Sbas correction. Sbas correction integration. So let's talk about the satellite. So satellite atomic clocks are highly accurate but still subject to drift. So this is the formula used to understand the model. So Sbas constantly monitor satellites via reference station and the real-time correction broadcast to reduce drift induced position error. So between 1 to 2 meters. And next is ionospheric delay model, which is caused by signal refraction in the ionospheric due to charge of particles. So this is the formula used for delay formula. So Sbas used initial models, which is 350 km altitude, to simplify the computation. The ionospheric grid points IGP defined across the surface area. And next is the delay correction interval from nearest IGP and map using this type of formula, using a Selen delay. Sbas reduced ionospheric error up to 85%. Next is the tropospheric delay modeling, which is caused by atmospheric refraction in the lower atmosphere and its non-diapers, which affect all the GNS frequency equally. So this is the model of the tropospheric delay modeling, which is using a Sasta-Moynihan model. And hydrostatic delay, which is 90% is stable, weight delay is more variable. While Sbas doesn't provide a real-time tropospheric correction, margins are applied for integrity. Next is the multipass reservoir noise modeling. So multipass is a signal reflection of nearby surface cause delay signals, modeled as a zero mean Gaussian distribution. The reservoir noise also modeled as Gaussian affected by SNR and bandwidth. It cannot directly corrected by Sbas, but effects considered in protection level. So the mitigation method is advanced antenna design, multiple resistant signal processing, and also receiver quality filtering algorithm. And last but not least is the Sbas correction integration. So Sbas system components, which has three types: wide area reference station WRS, master control center, and geostationary satellites. So how does it work is that WRS monitor GPS signal and measure satellite related errors. The MCC processor measure using real-time models. The correction and integrity data are uplinked to GEO satellites. The GEO rebroadcast the Sbas message on the same GPS L1 frequency. Sbas does enhance the user accuracy from 5 to 10 millimeter raw of GPS into 1 to 2 meter. Also, the signal space ranging error SISRE benchmark, which is lower than 1 meter.
Moving on to the system implementation. For SBAS, SBAS enhance the performance of GPS by providing real-time correction for errors such as ionospheric delay, satellite clock drift, and orbital inaccuracies. It significantly improved the GPS accuracy from around 5 to 10 meters to about 1 to 2 meters. SBAS operate using a network of ground-based reference stations placed at known location. This station monitor GPS satellite signal and detect any discrepancies. The collected error data is sent to the central master control center, where it is processed using algorithm to generate correction message and integrity alert. These correction messages are then sent to geostationary satellite, which broadcasts them back to the user on the same frequency as the GPS. SBAS enable receiver decode the signal and apply the correction to improve their positioning accuracy and ensure signal integrity. The SBAS error correction. For first ionospheric delay, corrected using the grid-based model with ionospheric grid point, or we call IGPS, and reducing one of the largest GPS error sources. Second, tropospheric delay, model based on satellite angle and user location to account for weather-related signal delay. For third, satellite clock error, SBS provide time offset correction to improve timing precision. Fourth, orbit, or we call MFERIS error, delta correction adjusts satellite position data for better location accuracy. And lastly, integrity information. SBAS continuously monitor GPS satellite and warn user if a satellite is unreliable. Next is for the differential GPS, or we call DGPS. So DGPS enhance standard GPS accuracy from plus minus 10 meter to about plus minus 1 to 3 meter by using correction data from ground-based reference station with known location. This station compare their true position with GPS derived position to calculate signal error. The computed correction are broadcast to nearby mobile receiver via radio or data links, allowing them to adjust their own GPS data in real time. For the key feature, accuracy typically around 1 to 3 meters, effective range up to 100 to 300 km from reference station, but limitation, accuracy decrease with distance from the station. So extended coverage achieved via CORS network or wide area DGPS, or we call WADGPS. For comparison of DGPS and SBAS, DGPS is more localized, simpler setup, real-time correction via nearby station, while SBAS, wide area coverage using satellite broadcast, better vertical accuracy and ideal for aviation. So next is extended Kalman filter or EKF. The extended Kalman filter is advanced algorithm used to estimate the state of dynamic nonlinear system in GPS application. EKF enhance accuracy by combining GPS data with reading from onboard sensor like accelerometer, gyroscope, magnetometer and IMUs. So for the key features, handles nonlinear system, use linearization to estimate state, sensor fusion, integrate multiple sensor, recursive prediction and update, continuously predict motion and correct with actual sensor or GPS data. Lastly, smooth noisy GPS signal.
Now let's move on to the validation summary Sbas performance analysis. So in this part, we're using the evolution of orbit and atmospheric correction from 5 Sbas surveys. So we have WAS, IGNOS, MSAS, DJN and SDCM. So in this paper, it shows that SDCM is the most accurate while EGNOS is highly reliable. Both of them has 0.634 meter and 0.645 meter. The WAS is slightly less precise, which is 0.8 to 0.9 meter, and the MSAS and GAN over 1 meter impact by regional atmospheric variability. Sbas excel at correcting satellite clocks and orbital error and model atmospheric delay using a GP. As conclusion, it shows that Sbas offers strong wide area correction with EGNOS and SDCM leading in precision. Next is the validation summary for DGPS field implementation. So, this using a precision agriculture robot in Morocco using a low-cost GPS receiver. So, as the methodology, he used a base station established for known coordinates and using a correction applied using a post-processing, which is a Timble Business Center. So, as a finding, the raw GPS accuracy is around 2 to 4 meters, and by using a DGPS corrected accuracy, it can correct up to 0.9 meter average, significantly reduce the literal longitude path deviation, and as a conclusion, DGPS provide affordable local correction and especially useful in rural or agriculture zone. Last but not least is the validation summary for EKF with multi-sensor fusion. So this paper use enhancing GPS position estimation using multi-sensor fusion and EKF. It also has a sensor IMU, GPS and LiDAR. So as for performance, using a GPS and IMU only, it shows that it has around 2.68 meter RMS error. But using GPS, IMU and LiDAR, this combination of three type of sensor, it shows that it has around 0.126 meter of RMS error, which show you the 95.2% improvement. So as a conclusion, EKF enable continuous accurate tracking even in GPS degraded or dynamic environment.
Now, let's move on to real-life application for SBAS. It is used in a wide range of real-life application, including autonomous vehicle, land level road navigation, low-flying UAVs, railway system, aviation, and precision agriculture. SBAS enhanced GNSS reliability and safety, making it especially valuable in aviation, where it supports precision landing even at smaller airports without ILS infrastructure. Next is the extended Kalman filter that are widely used in autonomous navigation system, where it combines GPS data with IMU, gyroscope, odometry and vision sensor for robust and accurate localization. And lastly is the DGPS. DGPS is primarily used in maritime navigation, hydrographic surveying, offshore drilling, land surveying, and precision farming, where higher positional accuracy is essential. So, as a conclusion, the Global Positioning System (GPS) is essential for modern navigation, but is affected by various sources such as ionospheric and tropospheric delay. Therefore, this project demonstrates how the satellite-based augmentation system significantly reduced this area through mathematical modeling and closed-loop correction system that use ground-based reference station and geostationary satellite. As GNSS technology continue to evolve with multi-frequency and multi-constellation capabilities, SBAS remains a vital component for delivering accurate, reliable, and global navigation services, emphasizing the ongoing importance of real-time GPS error mitigation. That's all from us. Thank you.